Dear students, today I am going to discuss the boiling heat transfer, and this is also very important topic as far as the heat transfer course is concerned. So let's first understand the definition of boiling and all that, and types of boiling. So as far as this boiling is concerned, let me tell you, the boiling will happen at solid liquid interface. The condition for the boiling is if solid temperature Tw is greater than the saturation temperature of the liquid, then boiling will take place. Saturation temperature of the liquid at 1 atmosphere is 100 degrees Celsius. So you know water boils at 100 degrees Celsius. What does it mean that Tw minus Ts is the driving force for boiling? Tw minus Ts means surface temperature, solid surface temperature minus saturation temperature of the liquid is the boiling heat transfer, boiling heat transfer driving force. Now this boiling could be of two types, namely pool boiling and second one is flow boiling. This is very broad, simple classification. Flow boiling. Now, pool boiling, as far as pool boiling is concerned, liquid or fluid, bulk velocity is zero. Okay, there could be some movement in the fluid microscopically, but there is no movement at the bulk level, right? Now, as far as flow boiling is concerned, flow boiling means the bulk fluid will move with some finite velocity. So, bulk of the fluid would be some finite. Now, this is the definition of boiling. Definition of boiling, it will happen at solid liquid interface. And the condition for boiling is the solid surface temperature must be greater than the saturation temperature of the liquid, means the difference between these two temperatures, meaning surface temperature of the solid Tw minus Ts is the boiling heat transfer driving force, right? And as far as types of boilings are concerned, since you are boiling the liquid may be stationary at a bulk level or liquid must be moving. So in both cases, if it is stationary and you are heating it up for boiling purpose and liquid is stationary at a bulk level, microscopic movement is there though, then it is called a pool boiling, while if it is moving with some finite velocity at a bulk level, then it's called the flow boiling. So this is the type of boiling and boiling definition and the condition of boiling. Now let's move to understand the difference between boiling and evaporation. You know, in boiling also liquid will convert into the vapor. Liquid will convert into the vapor. And in evaporation as well, you will find that liquid is converted into vapor. Is phase change. Both are phase change process. So what is the difference between these two? Let me explain with a figure. So this is suppose a vessel, and at the bottom of the vessel we are heating it up. We are heating means of providing some heat flux right there at the bottom. Now the liquid molecule near the surface, and suppose I am taking temperature less than the saturation temperature, less than the saturation temperature. Liquid temperature is less than the saturation temperature. Saturation temperature of the liquid at 1 atmosphere is 100 degrees Celsius. So let's say we are taking 60 degrees Celsius. So what will happen if you heat it up from the bottom? Heat it up from the bottom, then you will find that there is natural convection current will be established. Okay, because bottom surface is hot enough, so heat will transfer from the bottom surface to the liquid through convection. Okay, means the nearby layers of the molecules, the density of nearby layers of the molecules will decrease because you are increasing the temperature. And since there is a decrease in density, you will find that there is a buoyancy force upward active, and those buoyancy force m- made all the molecules to move up and reach to the surface. Now, this is the natural convection. Now, since hot molecules move upward, so a gap would be created, a vacancy would be created at that place. So that vacancy means there is no molecule. If there is no molecule, and you know that pressure is defined at the collision of the molecules. So no molecules, no pressure, so less pressure there. So due to pressure difference, from the top molecules will come down, because there is a almost no pressure at that very point, and at the upper layers high pressure. So due to pressure difference, the molecules will move from top to bottom, and hot molecules move from bottom to top. So this is, a current will be established, that is called the natural convection current. And if air is moving at the top of the surface, at the top of the free surface of the liquid. Free surface means the surface that is in contact with the air, top surface. So this top surface is in contact with the air. So air will remove some liquid molecules and carry with it in the form of vapor. That's called the evaporation. So evaporation will happen at the liquid gas interface, right? And boiling will happen at the solid and liquid interface. Suppose you are heating in the same vessel, but now your liquid at the saturation temperature, let's say 100 degrees Celsius. So you need to give heat in such a way that this surface temperature, solid surface temperature, must be greater than 100 degrees Celsius. Then only heat will be transferred from the wall to the liquid molecules. So once it will transfer from the wall to the liquid molecule, and suppose there are some nucleation sites are there at the surface. The nucleation sites, so liquid will be converted into. Let me draw the figure. Suppose you have, this is your vessel, and you are heating it from the bottom. All right. Now this surface, bottom surface is rough somewhere like this. Okay. So these are called the nucleation site. So once water will be converted, now this is at saturation temperature liquid, and this wall surface temperature, bottom surface temperature is wall surface temperature. Sometimes we call it. Now, since Ts minus Tw minus Ts, the driving force for the boiling. Now, what happens once water will be converted into vapor? Then it will trapped in this rough surface, nucleation site. So this water vapor will be trapped and liquid film outside. Please make a point that this since water vapor is trapped and liquid outside as a film, so this is the bubble. But this bubble will not contain air inside it. Okay, very interesting. This bubble will not contain air inside it. This bubble will contain water vapor inside it. So water vapor inside, and the water film outside. So both are liquid film outside and liquid vapor inside. So very interesting bubble will be created. And from fluid mechanics, that once bubble is created, then this inside pressure at the interface of the bubble, this inside pressure and the outside pressure must balance to each other. Okay, if anyone will be moved, then so this pressure difference, now due to surface tension, this bubble has been created. Now what is the formula? So P inside will be greater than P outside, that's why the bubble size is increasing. So P inside outside is equal to 4 sigma by R is the radius of bubble. So just need to understand, if this is inversely proportional to R, means if you need large size bubble, if you need large size bubble means high radius, so it's inversely proportional. So these pressure difference must be lower. Okay, so pressure difference must be lower for large size bubble. And since pressure is connected to temperature, so you can think of the sizing of the bubble is very much related to the temperature inside the bubble. Now, so this at this nucleation site, this bubbles are created, and if these bubbles, this is the water vapor inside it, and water vapor inside it. So due to its density differentiation, it will move up. It will move up. Now, if this temperature outside liquid temperature, its outside liquid temperature is comparably equal. If it is much less, then heat will be transferred from this paper bubble to the liquid, and this bubble would collapse. Now, bubble would collapse in many ways, but due to heat transfer, if liquid has a very less temperature than saturation temperature, then bubble formed at the bottom at the nucleation site will not reach to the top. Why? Why? Because less liquid has less temperature than the saturation temperature. So there is a high driving force for the heat transfer. So the heat will transfer from the vapor bubble to the liquid bubble inside the liquid itself. Once heat is transferred, then bubble will collapse and bubble will not reach at the surface. And there might be some cases when bubble formed and it will reach the surface, and at the surface it will be converted into vapor evaporation, through evaporation surface phenomenon, and it will mix up with the air. So bubble will be created. So there are three extreme conditions I am discussing. The first condition, that no bubble formation at all. Simply you are heating the liquid, and temperature difference with Tw minus Ts is not too much large that bubble formation would take place. But Tw is slightly larger than the Ts. So what happens, that natural convection current will be established, but this driving force is not sufficient to form the bubble. So there would be very less temperature T. Now after that, you will have the saturation temperature. Your liquid could be at the saturation temperature and or less than saturation temperature, and at the saturation temperature, and liquid could be more than saturation temperature. There are three cases possible. So based on that, there are different boiling regimes are there. So I am going to discuss. So now you just try to understand that, suppose this is the now in this phenomena, you see that your bulk of the liquid is not moving. Bulk of the liquid is not moving. So this is the cool boiling. And you suppose you have the pipe and fluid is flowing, and you are heating this pipe, providing some constant heat flux to the pipe outside the wall. So what will happen? You are boiling the liquid, and liquid is moving itself with some bulk velocity. So this is the type of boiling called flow boiling. Now we are discussing the pool boiling because it is easy to experiment with. So what we are going to do, suppose we are taking in this vessel pool of liquid. Liquid is stationary here at the bulk. This is the free surface. So what happens? Suppose you are heating, and this is the solid surface, bottom solid surface at temperature, some temperature Tw. Now what happens? That bubble is formed right here, and it will move up, up, up. Okay. So now this liquid temperature. Suppose this is water you are taking. This water temperature could be at saturation temperature, or could be less than saturation temperature. Less than saturation temperature. So less than saturation temperature means subcooled liquid, means subcooled liquid, and at saturation saturated liquid means this is, and boiling in this condition, and water is at saturation temperature called saturation boiling, and this when the saturation temperature of liquid is less than when the temperature of the liquid is less than saturation temperature, when the temperature of the liquid is less than saturation temperature, the liquid is in subcooled state. That's why the boiling in this condition will be called subcooled boiling. Subcooled boiling. Now, once you increase more temperature, this TW more increase, the TW and TS difference will increase. So more and more bubble will form, and sometimes these bubbles will form the slump. So many bubbles. So these are the different conditions. Okay. So this TW must be greater than TS saturation temperature. Then only boiling will take place. So TW must be greater than TS. So water saturation temperature at atmospheric pressure is 100 degrees Celsius. Now this this thing you must understand, right? So, and the second thing, what I told you that suppose this you are heating the liquid from the bottom. Okay, it is now bubble is formed at the surface. Will it reach to the free surface or not? Will depend on what. If your T bulk temperature is less than T saturation temperature. T saturation temperature is 100 degrees Celsius at 1 atmospheric pressure. Suppose you are taking at 80 degrees Celsius. T bulk temperature is 80 degrees Celsius. Now what will happen? Now T surface temperature, this TW must be higher, then only heat transfer will take place. Suppose you are taking this as 120 degrees Celsius. Now in this condition, what will happen? This bubble will move up, and second condition I will take. This is the second condition. Air bubble is formed at the bottom. Yes, it will move up, 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 and it will reach at the surface. But here, what is the condition? Here you have taken the T is temperature T saturated of the liquid, and this is, let's take both. TW is 120 degrees Celsius. Now see the different. Now see, if your temperature, bulk temperature is less, then heat trans. If it move up slightly due to buoyancy force, but T saturation is less. T bulk is less than T saturation, so there is larger driving force in this case than in this case. Okay, in this case, larger driving force for heat transfer. So heat from the vapor bubble will transfer to the liquid, and so bubble will collapse and will not reach to the surface. While in this case, since the bulk of the temperature, bulk fluid temperature reached up to the state of desaturation temperature, so there are not much driving force. This will extract all the heats of the vapor bubble, so vapor will reach at the surface. So these are the two conditions that you understand. Now here, as far as that this is considered, keeping TW is constant, see TW minus T saturation is the driving force. So if we increase the TW, okay, then difference will be increasing. So TW minus T sat is the driving force I told you earlier. Now let's have a look into the boiling phenomenon, boiling curve. This is the typical boiling curve. Now, at the x-axis, we have taken TW minus TS, So Ts is the saturation temperature and Tw is the surface temperature. Now heat flux in watt per meter square at the y-axis. Now from O to A, if you look into, then O to A, you will find that temperature difference is very less. So X, this is the temperature difference, so very less temperature difference driving force. Simply natural convection will happen. Bubble will not form at all. So you will find the linear graph from O to A. This point is, let's say, origin O. Okay, O to A. Now, at point A, you will find that some bubble formation will take place. Bubble formation will start, means this is the onset of bubble formation. The first very bubble will be formed at point A. At point A, okay, and so this is called, since the formation of bubble has started, this is called the nucleating process. So nucleation started right here. Okay, so A to B region is called the nucleate boiling region. We see the slope of the nucleate boiling region. Slope of the nucleate boiling region is much higher. Much higher slope means much higher slope. So heat flux is increasing very fast than the natural convection. Why? Because bubble formation and bubble moving up, this will create a lot of mixing in the fluid and that will enhance the heat transfer. So heat flux is increasing but at much faster rate in the nucleate boiling region. But you see in this region, and then slope will slightly go downwards as like that. Okay, so at this point, this is the point of inflection here. The slope is changing in this way. Okay, and the slope is then sorted in other way around. So at this point, what happened that enough bubble, now bubble, more and more bubbles are created, more and more bubbles are created. But then you see the slope is decreasing beyond this in the second V reason. Slope is decreasing means heat flux will slightly decrease because number of bubbles increases. Some bubble will collide and some bubbles will coalesce and will not reach to the surface. Now at very point B, once heat flux is reached, what you will find at very point B, heat flux is maximum. This is correspond to the maximum point, and this maximum point is called the critical heat flux, because at this heat flux, what will you find that more and more bubbles, water bubbles will form, and they will entirely cover the bottom solid surface of the vessel. So a film is created, and that film will create a resistance for the heat transfer. So heat transfer rate will further decrease in this direction. And since the film formation takes place, so this is called the film boiling region. So heat transfer will decrease. So more and more layers once will form, you will find that another type of another mode of heat exchange will be possible. Another mode of heat transfer, that is radiation, will come into picture. So radiation heat transfer since will come into picture. So in the film boiling region itself, you will find the state. So this is the transition boiling region. Third is transition boiling region. This is, and then after radiation will come into picture, then you will find the film is become completely stable and radiation heat transfer will take place also. So by this, the heat flux will further increase and reach to the point D. So I have explained this phenomena and I have written it that you can read it. So from O to A, the wall temperature is not sufficient beyond T saturation to initiate bubble nucleation. So in this region, the heat from the wall is transferred by single phase free convection. That's what I told you. So I have written those points as well. So at point A, the first bubble appears on the surface. So this is the called the onset of nucleate boiling. Now A to B, you will find many bubbles are formed in the A to B region. A to B region. This is the nucleate region, nucleate boiling region. In this region, you will find many bubbles are formed and grow at the wall. and detach from the wall under the effect of buoyancy, and the heat transfer regime is called the nucleate boiling. Now, bubbles create a lot of agitation and mixing near the wall, which enhances heat transfer. As a result, nucleate boiling is much more effective mechanism than free convection, as suggested by higher slope of the boiling curve. See the slope of the boiling curve in this second region. In this second region, you will find the slope of the boiling curve is much higher than the natural convection region. Okay, so this is the A to B. Now B to C, if you move B to C, I have explained this from B to C region at a critical high value of heat flux at the point B itself. I have explained thing at the point this B, maximum critical heat flux region at the point. So at a critical value of heat flux, there is so many bubbles from the crowding at the wall that they can merge and form a continuous stable vapor film. Thus, there is sudden transition from nucleate boiling to film boiling. Since there is a transition happens in third region from nucleate boiling to film boiling, so this is called the transition boiling region from B to C. Okay, so and the sudden transition is called the departure from nucleated boiling (DNB) or critical heat flux or burnout or boiling crisis, and is associated with a drastic reduction in the heat transfer coefficient, because vapor is a poor conductor of heat, because the conductivity of vapor is less than the liquid. So vapor is a poor conductor of the heat, so it will create the more resistance to the heat transfer. Consequently, the wall temperature increases abruptly and dramatically, and this may result to physical destruction of the heater, because you see transition boiling on the x-axis you are moving in forward direction, so TW minus TS further has increased. So since this is declining, heat flux is declining at much faster rate, and hence TW minus TS. So your TW minus TS is increasing in this x direction, so wall temperature will increase abruptly, and you will find that which may result in physical destruction of the heater itself, vessel itself. And beyond C point, since I told you that radiation will happen, so heat transfer, heat flux will further increase. And so this is the film boiling reason, of course, but heat transfer from the walls occur mostly by convection within the vapor film and radiation across the vapor film. So this is the explanation of, and this is called the boiling curve. So this is all about the boiling curve, boiling heat transfer. So I will upload this notes as well in the class, Google Classroom. Thank you so much. I have covered almost all the syllabus of the heat transfer. Whatever left, we will cover in the offline now. Okay, when your people will come into the college. Okay, and some doubt removal classes as well. Thank you so much. All the best. Good day.